So good morning all. In this section we will see a special case of the previous derivation which was there in the previous videos. Okay, so here we will consider two medium. First medium is perfect dielectric and the second medium is a perfect conductor, and this is a boundary of the two medium. And perfect dielectric, the conductivity is 0, attenuation is 0, and gamma 1 is equal to alpha 1 plus j beta 1. Since alpha is 0, gamma is equal to j beta 1. And coming to the second medium, it is a perfect conductor, that means sigma 2 is equal to infinity, and eta 2, the intrinsic impedance, is equal to 0 for a perfect conductor, because this is a general expression of eta, that is eta is equal to square root of j omega mu by sigma plus j omega epsilon. Since sigma is equal to infinity, what happens to this intrinsic impedance? It will be nearly equal to 0. That is why we have taken the intrinsic impedance of the perfect conductor as 0. Okay. Now in the earlier video we derived the reflection coefficient as eta 2 minus eta 1 by eta 2 plus eta 1, and in this special case the value of eta 2 is equal to 0. So if you substitute eta 2 equal to 0 in this expression, then you will get the reflection coefficient as minus 1. Then we have a relation connecting the reflection coefficient and transmission coefficient as tau is equal to 1 plus the reflection coefficient. This is your transmission coefficient and this is your reflection coefficient, and this relation is also very important, the relation connecting reflection coefficient and the transmission coefficient. Okay, so you got the reflection coefficient as minus 1. So if you substitute it in the relation tau is equal to 1 plus reflection coefficient, then you will get tau, which is our transmission coefficient, as 0. So I repeat, in this special case where the first medium is perfect dielectric and second medium is perfect conductor, the reflection coefficient is minus 1 and the transmission coefficient is 0. Transmission coefficient 0 indicates that the wave is not transmitted. The wave is not transmitted. That means there will be no electromagnetic wave in this second medium, because the incident wave and the reflected wave lies in the first medium and the transmitted wave lies in the second medium. So in this special case, since the reflection coefficient, the transmission coefficient is equal to 0, there will be no transmitted wave, only reflected wave will be there, whose reflection coefficient is minus 1. The totally reflected wave combines with the incident wave to form a standing wave. So as I said earlier, here there will be no transmitted wave, only you will be having the incident one and the reflected one. So what happens is these two waves combine together to form a standing wave. So I can say incident wave plus reflective wave forms a standing wave. A standing wave stands, it does not travel. Okay. Now this standing wave has only two components, which are the incident electric field and reflected electric field. Similarly, incident magnetic field and reflected magnetic field. It doesn't have any transmitted wave components in both electric and magnetic field. It will not be having any transmitted components. So I'll just redraw the same figure with more clarity. That is, the first medium is a dielectric, second medium is perfect conductor. This is the xy plane, your boundary, this is the z axis, and this is your incident wave, this is your reflected wave, and beta 1 is the propagation constant of first one, beta 2 that of second one, and perfect conductor, you know the electric field is equal to 0. We already studied that the electric field inside a perfect conductor is equal to 0. Now we know what is EI. We already saw this in the earlier derivations, that is EI is equal to EI naught into e raised to minus j beta 1 Z. Z represents the direction of electromagnetic wave. So in the earlier derivation, we assumed that the electromagnetic waves are traveling in Z direction, and here you can see a negative sign because electromagnetic wave is along the positive Z axis. Now next we will write the expression for ER, which is our reflected wave, that is given by ER is equal to ER naught into e raised to j beta 1 Z. Again, here you can see beta 1 is a propagation constant because reflected wave is also in the first medium, and here the exponential term is positive because you can see the reflected wave is moving along the negative Z direction. That is why here the exponential term is positive. Now you know the total electric field of the standing wave, it can be written as Et of Z is equal to Ei plus Er. That is equal to Ei naught e raised to exponential of minus j beta 1 Z plus Er naught into exponential of j into beta 1 Z. That is my equation 11. Okay. Now in the previous derivation I told you that that is the electromagnetic wave is traveling in the Z direction, and we took the electric field along the X axis and magnetic field along the Y axis. Okay, so for incident wave and reflected wave, and I told you that since the electromagnetic wave is traveling along the Z axis, that component is perpendicular to the boundary. It is coming like this and your boundary is like this. So electromagnetic wave is perpendicular to the boundary. That means this electric field and magnetic field is parallel or tangential to the boundary, like this, tangential to the boundary. So I repeat, in this case where I have taken electromagnetic wave propagating along the Z axis, I can say electromagnetic wave is a perpendicular component while the remaining two components E and H are parallel to the boundary. So according to the boundary condition of electromagnetic field, I can write that EI plus ER is equal to ET, where EI is a tangential component of my incident wave, ER is a tangential component of reflected wave, and ET is a tangential component of transmitted wave. But in this particular condition we don't have ET. ET is equal to 0. So I can write EI is equal to minus ER. Since EI is equal to minus ER, this EI naught is also equal to minus ER naught. Okay, that is as I said earlier, that is, this is your incident wave. So the incident wave is falling on the boundary of your first medium. Since the second medium boundary of your two mediums, since the second medium is conductor, what happens, there will be no transmitted wave across the second medium. The entire wave which is incident across the boundary gets reflected back. This is your reflecting wave, reflected back to the first medium itself. And this incident wave and reflected wave should be of same amplitude. Then only you can say that a standing wave is formed. But the incident wave and reflected wave will be opposite to each other. That means there will be a phase shift. That is why here we got the condition EI is equal to minus ER, or EI naught is equal to minus ER naught. Now what I am going to do is I am going to substitute this condition in equation 11 so that I can write ET of Z is equal to EI naught into e raised to minus j beta 1 Z, and instead of ER naught I am going to substitute minus of EI naught. So minus EI naught into e raised to j beta 1 z. Okay. So what I did is I applied this condition on my 11th equation. Okay, so finally equation 11 is something like this: et of z is equal to ei naught into e raised to minus j beta 1 z minus ei naught e raised to j beta 1 z. So I have taken ei naught outside. So I will get e raised to j beta 1 z minus e raised to j beta 1 z. And then what I am going to do is I am going to multiply and divide the numerator and denominator by 2j term, so that I can use the identity e raised to ix minus e raised to minus ix by 2i is equal to sin x. So to convert this term into sin x term, I am multiplying the numerator and denominator by 2j, so that finally I can write et of z is equal to minus 2j ei naught sin beta 1 z of ax, because here we have taken the electric field along the x-axis. So the unit vector will be along the x-axis. The electric field is along the x-axis. So finally I will get et of z is equal to minus 2j ei naught sin beta 1 z ax. Here we got a minus sign because the sin x is e raised to ix minus e raised to minus ix by 2i, but in this expression we are having e raised to minus j beta 1 as our first term. So that is why here we got a minus sign. Now in sinusoidal time variation, what I am going to do is I am going to add a time factor e raised to j omega t along this expression, so that I can write et of z comma t is equal to minus 2j ei naught sin beta 1 z into e raised to j omega t. Then you know what is e raised to j omega t, that is cos omega t plus j sin omega t, that I am substituting. Then what I am going to do is I have removed the bracket. So when I remove the bracket, finally I will get 2 ei naught sin beta 1 z sin omega t minus 2j ei naught sin beta 1 z cos omega t ax. So in the next step I am writing et z comma t equals real part of et of z comma t, so that finally we will get what this term only. The real part of et of z comma t is the first term, and the imaginary part of et z comma t is the second term, but here we need only the real part of et of z comma t. So I have written as et z comma t is equal to real part of et z comma t, so that I can write the total electric field of the standing wave is this first term 2 into ei naught sin beta 1 z sin omega t ax. Similarly, you can derive the expression for ht z comma t as 2 hi naught cos beta 1 z cos omega t ay, because here our magnetic field is along the y-axis, and that derivation you can do as self-study. And that's all. Thank you.